In the depths of space, two invisible titans are locked in an eternal battle for control of reality itself. One force pulls everything together, weaving the cosmic web that connects galaxies across billions of light years. The other pushes everything apart with such relentless power that it will eventually tear the universe into cold, empty darkness. These forces have been fighting since the moment of creation, and their struggle determines whether our cosmos will live or die. You cannot see them, touch them, or detect them directly, yet together they control 95% of everything that exists. Dark matter and dark energy represent the greatest mystery in physics, challenging every assumption we have made about the nature of reality. One builds the scaffolding upon which all cosmic structure depends. The other drives an acceleration so violent it defies our most fundamental equations. If you are ready to journey into the invisible universe that surrounds us, hit that like button and subscribe. What we are about to discover will change how you see every star in the night sky. Prepare yourselves. We begin. Imagine standing in a vast cathedral where 95% of the architecture remains completely invisible. You can see the beautiful stained glass windows and ornate pillars, but the foundation, walls, and ceiling that hold everything together are made of materials your eyes cannot perceive. This is our universe. Everything you have ever seen, from Earth to the most distant galaxies captured by our most powerful telescopes, represents only 5% of cosmic reality. The remaining 95% consists of two mysterious components that operate according to rules we barely understand. Dark matter comprises 27% of the universe, providing the invisible scaffolding that holds galaxies together and guides the formation of cosmic structure. Dark energy dominates everything else at 68%, driving an acceleration of space itself that grows stronger with each passing moment. These numbers are not rough estimates or educated guesses. They represent some of the most precise measurements in the history of science, confirmed by multiple independent observations spanning decades of research. Satellites have mapped the afterglow of the Big Bang with extraordinary detail. Telescopes have tracked the motion of billions of galaxies across cosmic time. Underground laboratories have pushed the limits of detection technology, searching for dark matter particles. Every measurement points to the same unsettling conclusion. We live in a universe dominated by forces we cannot directly observe, composed of materials we have never identified, operating through mechanisms that challenge our most basic understanding of physics. The visible cosmos that inspired poets and philosophers throughout human history turns out to be little more than foam on an ocean of invisible reality. Dark matter reveals itself through gravitational effects that cannot be explained by ordinary matter alone. When astronomers measure how fast stars orbit around galaxy centers, they find something impossible. Stars in the outer regions of galaxies move far too quickly to remain bound by the gravitational pull of visible matter. According to Newton's laws, these stars should have been flung into intergalactic space billions of years ago. Yet there they are, following stable orbits as if held in place by enormous amounts of invisible mass. Galaxy clusters provide even more dramatic evidence. These cosmic cities containing thousands of galaxies are held together by gravitational forces requiring 10 times more matter than telescopes can detect. Hot gas between cluster galaxies reaches temperatures of millions of degrees, moving at speeds that would escape the cluster entirely if only visible matter were present. The invisible mass needed to contain this gas dwarfs all the stars and planets combined. Gravitational lensing offers perhaps the most compelling proof that dark matter exists as a physical substance rather than a modification of gravitational laws. Massive galaxy clusters bend space and time so severely that they act like cosmic magnifying glasses, distorting the appearance of background galaxies into arcs and multiple images. The amount of distortion reveals exactly how much matter is present, and the answer always exceeds visible matter by enormous factors. Most remarkably, colliding galaxy clusters have separated the locations of visible and dark matter, providing direct evidence that dark matter exists independently of ordinary matter. When two massive clusters crash together at millions of miles per hour, the hot gas between galaxies interacts and slows down through friction, but the dark matter passes through unchanged, continuing on separate trajectories revealed through gravitational lensing maps. The nature of dark matter particles remains one of physics' greatest puzzles. These particles must interact gravitationally to form the cosmic web, but they cannot interact electromagnetically, or they would emit light and cease to be dark. They cannot interact strongly with ordinary matter, or we would have detected them in laboratory experiments. This combination of properties suggests exotic particles unlike anything in the standard model of particle physics. Leading candidates include weakly interacting massive particles that interact only through gravity and the weak nuclear force. These hypothetical particles would have been created in enormous quantities during the first moments after the Big Bang, then persisted essentially unchanged as the universe expanded and cooled. Axions represent another possibility, incredibly light particles that could permeate all of space while remaining effectively invisible to detection. Underground laboratories around the world are pushing detection technology to its absolute limits in hopes of catching dark matter particles. The LX Zeppelin experiment operates nearly a mile beneath the Earth's surface, using 7 tons of liquid xenon as both target and detector. When a dark matter particle potentially collides with a xenon nucleus, it should produce a tiny flash of light and electrical signal that can be measured with extraordinary precision. The experiment has analysed hundreds of days of data without detecting a single confirmed dark matter interaction. This absence of detection is itself scientifically valuable, ruling out entire classes of dark matter candidates and forcing theorists to consider more exotic possibilities. Each null result constrains the properties these particles can have, gradually narrowing the parameter space where dark matter might hide. Alternative approaches search for axions using sophisticated radio techniques that can scan thousands of potential particle masses simultaneously. The BREAD experiment represents this new generation of broadband detectors, abandoning the targeted search strategies of previous experiments in favor of comprehensive surveys across vast ranges of possibility. While dark matter builds cosmic structure through gravitational attraction, dark energy tears it apart through a force that pushes against gravity itself. This mysterious component was discovered in 1998 through observations of distant supernovae that appeared fainter than expected. The only explanation for their dimness was that they were farther away than anticipated, indicating that cosmic expansion was accelerating rather than slowing under gravity influence. The discovery revolutionized cosmology and earned its discoverers the Nobel Prize in Physics. For the first time in human history, we had direct evidence that the universe contains a component that acts opposite to gravity, pushing space apart rather than pulling matter together. This force operates on the largest scales imaginable, affecting the expansion rate of space itself across billions of light-years. Dark energy behaves unlike any known form of matter or radiation. While ordinary matter becomes less dense as the universe expands, dark energy maintains constant density throughout cosmic growth. This means that dark energy influence grows stronger over time as space increases in volume, while dark energy density remains unchanged. Current expansion rates indicate that space doubles in size every 10 billion years, and this doubling rate continues accelerating. The nature of dark energy represents an even deeper mystery than dark matter. Leading theories suggest it might be vacuum energy arising from quantum fluctuations in empty space itself. According to quantum mechanics, even the vacuum of space teems with virtual particles that constantly appear and disappear, potentially creating a background energy density that drives cosmic acceleration. However, when physicists calculate the expected vacuum energy density, they get an answer that exceeds observations by more than 100 orders of magnitude. This represents the largest discrepancy between theory and observation in the history of physics, suggesting that our understanding of quantum mechanics, general relativity, or both requires fundamental revision. Alternative theories propose that dark energy represents a dynamic field that varies over time and space, similar to the field that drove cosmic inflation in the universe's earliest moments. This field might strengthen or weaken over cosmic time, creating expansion histories dramatically different from the simple constant acceleration we observe today. Recent observations from the Dark Energy Spectroscopic Instrument have provided tantalizing hints that dark energy might indeed be evolving. DESY has created the largest three-dimensional map of the universe ever constructed, analyzing the positions and motions of millions of galaxies across 11 billion years of cosmic history. The results suggest that dark energy was stronger in the past and has been gradually weakening over time. If confirmed, this discovery would represent one of the most significant developments in cosmology since the original detection of dark energy itself. Evolving dark energy opens entirely different possibilities for the universe fate, from eventual contraction in a big crunch to catastrophic acceleration that tears apart atoms themselves in a big rip. The battle between dark matter and dark energy plays out across cosmic time through competing processes that determine the universe's large-scale structure. Dark matter provides the gravitational wells where galaxies form and cluster together. Its invisible tendrils create the cosmic web that connects galaxy clusters across hundreds of millions of light-years. Dark energy opposes this structure formation by accelerating the expansion of space itself. During the universe's first several billion years, dark matter dominated cosmic evolution. Its gravitational influence pulled matter together into increasingly complex structures, from the first stars to massive galaxy clusters. The cosmic web grew richer and more elaborate as matter flowed along dark matter filaments toward the densest regions. But dark energy influence has grown stronger as the universe expanded and aged. Today, dark energy dominates cosmic dynamics at scales larger than several hundred million light-years. Beyond this distance, dark energy repulsive pressure overcomes gravitational attraction between matter concentrations, pushing cosmic structures apart despite their mutual attraction. This cosmic tug-of-war determines which galaxies we can observe and how long they remain visible. Galaxies within our local group remain gravitationally bound despite cosmic expansion, but galaxies in distant clusters are being carried away by dark energy at speeds that will eventually exceed light velocity, causing them to disappear beyond our cosmic horizon forever. The expansion history encoded in this battle reveals fundamental truths about cosmic evolution that extend far beyond astronomy. By measuring how the balance between dark matter and dark energy has shifted over time, scientists can test Einstein's theory of general relativity under extreme conditions and potentially discover physics beyond the standard model. Current observations suggest we live during a unique epoch in cosmic history when dark energy has recently begun to dominate but has not yet completely overwhelmed structure formation. Earlier in cosmic history, when the universe was smaller and denser, dark matter gravitational effects were stronger relative to dark energy. Later in cosmic history, dark energy will so completely dominate that no new structures will be able to form. This timing may not be coincidental. Some theories suggest that the emergence of complex structure and ultimately life requires a delicate balance between forces that build structure and forces that tear it apart. If dark energy had dominated too early, galaxies could never have formed. If it dominates too completely in the future, the universe will become cold and empty. The precision required to measure these competing forces pushes observational astronomy to its absolute limits. Scientists must track the positions and velocities of millions of galaxies with extraordinary accuracy, accounting for systematic errors that could masquerade as cosmic acceleration or dark matter effects. They must calibrate distance measurements across billions of light-years using standard candles whose properties are understood well enough to serve as cosmic rulers. Every major advance in telescope technology reveals new aspects of the dark universe. Space-based observatories avoid atmospheric distortion and can observe wavelengths of light that never reach the ground. Underground detectors shield sensitive instruments from cosmic rays and background radiation that could contaminate dark matter searches. Sophisticated computer simulations model how dark matter and dark energy should affect cosmic structure formation, providing theoretical frameworks against which observations can be tested. The stakes could not be higher. Understanding dark matter and dark energy will determine whether we can predict the universe's ultimate fate, whether we can unify quantum mechanics with general relativity, and whether physics requires revolutionary new concepts that extend beyond everything we currently understand about the nature of reality. The search for these invisible forces has revealed something even more disturbing than their mysterious nature. Our most precise measurements of cosmic expansion are giving contradictory results that threaten to shatter our understanding of reality itself. When scientists measure how fast the universe expands using nearby supernovae and variable stars, they get one answer. When they calculate the expansion rate using the cosmic microwave background from the early universe, they get a completely different result. This disagreement, known as the Hubble tension, represents more than a simple measurement error. Both techniques have been refined to extraordinary precision over decades of observation. Both should give identical answers if our theoretical models correctly describe cosmic evolution. Instead, they diverge by nearly 9%, a discrepancy so large and persistent that it suggests fundamental gaps in our understanding of how the universe works. The James Webb Space Telescope was supposed to resolve this crisis by providing the most precise distance measurements ever achieved. Instead, it has confirmed that the disagreement is real and cannot be explained away by observational uncertainties. Every new measurement strengthens the evidence that something is seriously wrong with our cosmic models. Local measurements consistently indicate that space expands at 73 kilometers per second for every megaparsec of distance. This means that galaxies separated by roughly 3 million light-years recede from each other at 73 kilometers per second due to cosmic expansion alone. But calculations based on conditions in the early universe predict an expansion rate of only 67 kilometers per second per megaparsec. The difference might seem small, but it has profound implications for everything we think we know about cosmic history. If the universe expands faster than predicted, it reaches its current size in less time, making the cosmos younger than we thought. Current calculations place the universe age at 13.8 billion years based on cosmic microwave background data. But if the higher local measurement represents the true expansion rate, the universe might be only 12.7 billion years old. This creates immediate conflicts with other observations. We can see stars in globular clusters that appear to be 13 billion years old, based on stellar evolution models. These ancient suns cannot be older than the universe itself, forcing scientists to question either their understanding of stellar physics or their measurements of cosmic expansion. The tension extends beyond simple age calculations to challenge our most successful theoretical framework. The lambda cold dark matter model has explained countless observations over the past 3 decades, from the patterns in cosmic microwave background radiation to the large-scale structure of galaxy clusters. Finding such a significant discrepancy threatens the entire edifice of modern cosmology. Several exotic explanations have emerged to resolve this crisis, each requiring physics beyond our current understanding. Early dark energy proposes that a brief burst of cosmic acceleration occurred shortly after the Big Bang, giving the universe an extra kick of expansion that would reconcile the conflicting measurements. This hypothetical energy component would have operated only during the first few 100,000 years of cosmic history before disappearing entirely. Modified gravity theories suggest that Einstein equations break down on cosmic scales, requiring additional terms that produce apparent acceleration without invoking mysterious dark energy. Some models propose that gravity becomes stronger at large distances, enhancing structure formation and potentially resolving multiple observational puzzles simultaneously. Alternative theories question whether dark energy exists at all, The timescape model argues that our measurements of cosmic acceleration might be illusions caused by the complex non-uniform structure of the universe rather than evidence for exotic energy components. This framework suggests that different regions of space literally experience time differently due to gravitational effects, leading to apparent acceleration without requiring new physics. The model proposes that clocks in dense regions like galaxy clusters would run slower than clocks in empty voids, creating systematic biases in how we measure distances and expansion rates. If true, this would mean that dark energy represents a misidentification of variations in cosmic expansion rather than a fundamental force-driving acceleration. Underground experiments searching for dark matter particles face their own mounting tensions. Decades of increasingly sensitive searches have failed to detect the weakly interacting massive particles that theory suggests should be colliding with detectors millions of times per day. Each null result forces scientists to consider more exotic possibilities or question whether dark matter consists of particles at all. The LUX Zeppelin experiment has achieved sensitivity nearly 5 times better than previous efforts, analysing hundreds of days of data from 7 tons of liquid xenon. The absence of any confirmed dark matter signals has ruled out entire classes of theoretical models, pushing the remaining candidates into parameter ranges that require increasingly contrived assumptions. Some researchers now propose that dark matter might consist of primordial black holes formed in the universe's earliest moments rather than exotic particles created in laboratory conditions. These microscopic black holes would interact only gravitationally, explaining why particle detectors have found nothing while still providing the invisible mass needed to hold galaxies together. Others suggest that dark matter might be composed of axions, hypothetical particles so light and weakly interacting that they would require completely different detection strategies. The BREAD experiment represents this new approach, using sophisticated radio techniques to search for axion interactions with electromagnetic fields across thousands of potential masses simultaneously. The failure to detect dark matter particles has led some physicists to question whether the phenomenon requires new particles at all. Modified Newtonian dynamics proposes that gravitational laws themselves change when accelerations become extremely small, naturally explaining galaxy rotation curves without invoking invisible matter. However, these alternative theories struggle to explain the full range of dark matter evidence, from gravitational lensing observations to the cosmic microwave background patterns that require dark matter to form the seeds of structure formation. The theoretical landscape remains divided between exotic particle explanations and modifications to fundamental physics. Meanwhile, observations of cosmic acceleration continue revealing unexpected complexities in dark energy behavior. The Dark Energy Spectroscopic Instrument has measured baryon acoustic oscillations with unprecedented precision, using the fossilized imprint of sound waves from the early universe as standard rulers across cosmic time. These measurements suggest that dark energy might not be the simple cosmological constant that Einstein originally proposed. Instead, the data hints at evolution over time, with dark energy potentially weakening from its peak strength billions of years ago. Such evolution would fundamentally alter our understanding of cosmic fate and require new theoretical frameworks to explain why dark energy changes. The statistical significance of these findings approaches the threshold that physicists consider definitive evidence for new physics. When combined with supernova observations and cosmic microwave background data, the evidence for evolving dark energy reaches nearly 4 sigma confidence, tantalizingly close to the 5 sigma standard required for claiming a discovery. If confirmed, evolving dark energy would open entirely different scenarios for the universe's ultimate destiny. Rather than the heat death predicted by constant dark energy, a weakening dark energy might eventually allow gravity to halt expansion and reverse it into a big crunch. Conversely, if dark energy strengthens over time, it could lead to a big rip that tears apart atoms themselves. The implications extend far beyond cosmology to fundamental physics itself. Dark energy evolution might reveal connections between cosmic acceleration and quantum field theory, potentially providing clues about how to unify general relativity with quantum mechanics. The energy scales involved in dark energy are so low that they probe physics in regimes completely inaccessible to terrestrial experiments. These mounting tensions and unexpected discoveries suggest that we stand at the threshold of a revolution in our understanding of cosmic reality. The invisible universe that dominates existence operates according to rules we have barely begun to comprehend, challenging our most basic assumptions about the nature of space, time, matter, and energy. The battle between dark matter and dark energy continues to unfold across cosmic scales and through cosmic time, shaping the fate of every galaxy we can observe. But the rules governing this battle may be far stranger and more complex than we ever imagined, requiring us to abandon comfortable theoretical frameworks and venture into uncharted territories of physics. The precision required to map this invisible battlefield has pushed modern astronomy into territories that would have seemed impossible just decades ago. Scientists are now tracking the motion of individual galaxies across billions of years of cosmic history, measuring changes in expansion rates with accuracy that approaches 1 part in 1,000. These measurements demand technological capabilities that operate at the very edge of what physics allows. The Vera Rubin Observatory will soon begin the most comprehensive survey of the night sky ever attempted, capturing images of the entire visible universe every few nights for 10 years. This relentless monitoring will reveal how dark energy influences cosmic structure across timescales that dwarf human civilization. Every supernova explosion, every galaxy collision, every subtle shift in cosmic expansion will be recorded and analyzed to extract clues about the invisible forces shaping reality. But the most disturbing aspect of these observations is not their technical complexity, it is what they reveal about the stability of the cosmos itself. The balance between dark matter construction and dark energy destruction appears far more delicate than anyone anticipated. Small changes in either force could have cascaded through cosmic history, preventing the formation of stars, galaxies, or ultimately life itself. This cosmic coincidence problem haunts theoretical physicists who struggle to explain why dark energy emerged as the dominant force precisely when it did. If dark energy had begun accelerating expansion just a few billion years earlier, the universe would have expanded so rapidly that matter could never have clumped together into stars and galaxies. The cosmic web would never have formed. Space would have remained cold, dark, and empty throughout eternity. Conversely, if dark energy had remained dormant for just a few billion years longer, gravity would have eventually halted cosmic expansion entirely. The universe would have collapsed back into a hot, dense state similar to the Big Bang, destroying every structure that had managed to form during its brief existence. The fact that we observe a universe balanced precisely between these extremes suggests either remarkable cosmic luck or fundamental physics we have yet to discover. Some theories propose anthropic selection, arguing that we observe this particular balance only because universes with different balances could not produce observers to study them. Other models suggest that dark energy and dark matter are connected through mechanisms that naturally maintain cosmic stability. Recent theoretical work has explored whether dark matter and dark energy might represent different aspects of a single, more fundamental phenomenon. These unified dark sector models propose that the same physics responsible for providing invisible mass also drives cosmic acceleration. Such connections could explain why both components emerged as dominant forces at roughly the same epoch in cosmic history. The search for these connections has led physicists to consider modifications of spacetime itself that operate differently across various scales and epochs. Some theories suggest that the dimensionality of space might change over cosmic time, with extra dimensions that were prominent in the early universe gradually becoming compactified or hidden as the cosmos evolved. Other models propose that the fundamental constants of nature themselves evolve over cosmic time. The strength of gravity, the speed of light, or the masses of elementary particles might have been different in the past, creating conditions that favored structure formation before transitioning to the acceleration-dominated epoch we observe today. These possibilities challenge the most basic assumptions underlying modern physics. If fundamental constants change over time, then the laws of physics themselves become dynamic rather than eternal principles. Laboratory experiments conducted today might reveal different results than identical experiments performed billions of years ago or billions of years in the future. The implications extend beyond academic curiosity to practical questions about the reliability of physical law. If the universe operates according to rules that change over cosmic time, then our understanding of reality based on local measurements might not apply to distant regions of space or different epochs in cosmic history. Advanced computer simulations attempt to model these possibilities by creating virtual universes with different combinations of dark matter and dark energy properties. These cosmic laboratories allow researchers to explore scenarios impossible to observe directly, testing how alternative physics would affect galaxy formation, star formation, and ultimately the emergence of complexity. The most sophisticated simulations now track individual dark matter particles across billions of years of cosmic evolution, revealing intricate details about how invisible matter flows along filaments and accumulates in galaxy halos. These virtual universes must reproduce not only the large-scale structure we observe today, but also the entire evolutionary history captured in observations of distant galaxies. When simulations successfully match observations, they provide confidence that our theoretical models capture essential aspects of cosmic evolution. When they fail to reproduce observed phenomena, they highlight gaps in our understanding that require new physics or alternative approaches. Recent simulations have struggled to explain several puzzling observations that suggest dark matter behavior might be more complex than simple gravitational interactions. Small satellite galaxies around the Milky Way appear to be distributed differently than simulations predict. The centers of some galaxies contain less dark matter than expected. These discrepancies might indicate that dark matter interacts with itself or ordinary matter through forces beyond gravity. Self-interacting dark matter models propose that dark matter particles can collide with each other, transferring energy and momentum in ways that alter how matter accumulates in galaxy centers. These interactions would be too weak to detect in laboratory experiments, but strong enough to affect cosmic structure formation over billions of years. Alternative explanations suggest that dark matter might decay over cosmic time, gradually disappearing and altering the gravitational landscape that holds galaxies together. Such decay would leave distinctive signatures in galaxy properties and cosmic structure that future observations might detect. The European Space Agency Euclid mission represents the next generation of dark energy investigations, designed to map the positions and shapes of billions of galaxies with unprecedented precision. This cosmic cartography will reveal how dark energy has influenced structure formation across different epochs, potentially distinguishing between constant and evolving dark energy models. Euclid measurements will also probe whether Einstein general relativity correctly describes gravitational physics on cosmic scales. If gravity operates differently than predicted, the patterns of galaxy clustering and gravitational lensing should deviate from theoretical expectations in measurable ways. The Nancy Grace Roman Space Telescope will extend these investigations even further, conducting surveys that could discover thousands of supernovae and measure their properties with extraordinary accuracy. These observations will trace the expansion history of the universe across cosmic time with enough precision to detect subtle variations in dark energy behavior. Ground-based facilities are pushing complementary approaches to even greater extremes. The next generation of extremely large telescopes will have mirrors spanning 30 to 40 meters in diameter, collecting enough light to study individual stars in galaxies billions of light-years away. These observations will provide independent checks on distance measurements and expansion rates. Underground dark matter laboratories continue expanding their sensitivity through ever more sophisticated shielding and detection techniques. The next generation of experiments will use hundreds of tons of target material, increasing their chances of detecting the incredibly rare interactions that dark matter particles might produce. Cryogenic detectors operating at temperatures just above absolute zero can detect the tiny amounts of heat deposited when dark matter particles collide with atomic nuclei. These devices represent the pinnacle of precision measurement, capable of sensing energy deposits equivalent to a single photon of visible light. Directional detection experiments attempt to measure not just the energy of dark matter interactions, but also the direction from which particles arrive. As Earth orbits the Sun and moves through the galaxy, it should encounter dark matter particles preferentially from specific directions related to our motion through the dark matter halo surrounding the Milky Way. The combination of multiple detection strategies offers the best hope for finally identifying dark matter particles and determining their properties. Once detected, these particles could be studied in detail to understand how they formed in the early universe and how they contribute to cosmic structure formation. But perhaps the most profound implications of dark matter and dark energy research extend beyond physics itself to questions about the nature of scientific knowledge and human understanding. We have constructed our entire worldview based on the 5% of reality that we can directly observe, building theories and models that might miss essential aspects of how the universe actually operates. The invisible universe surrounding us might operate according to principles so alien to human experience that our evolved intuitions and mathematical frameworks prove inadequate to comprehend them. We might be like inhabitants of a two-dimensional world trying to understand three-dimensional geometry, lacking the conceptual tools necessary to grasp higher dimensional reality. This epistemological challenge extends to practical questions about the limits of scientific discovery. If dark matter and dark energy represent phenomena fundamentally beyond direct observation, how can we ever achieve complete understanding? Are we doomed to infer their properties only through indirect effects, forever uncertain about their true nature? The history of physics suggests that revolutionary discoveries often emerge from precisely such mysterious phenomena that initially resist explanation. Electromagnetic radiation was once as mysterious as dark energy appears today. Quantum mechanics emerged from puzzling observations that classical physics could not explain. The pattern suggests that today invisible universe might yield tomorrow breakthrough insights. Advanced civilizations elsewhere in the cosmos face identical challenges in understanding dark matter and dark energy. These forces operate uniformly throughout the observable universe, creating the same puzzles for any intelligence capable of conducting precision astronomical observations. The solutions we discover might represent universal insights rather than parochial human perspectives. The search for dark matter and dark energy has already transformed our understanding of cosmic evolution and fundamental physics. These investigations have revealed that the universe is far stranger, more dynamic, and more mysterious than previous generations ever imagined. The forces that dominate cosmic evolution operate through mechanisms that challenge our most basic assumptions about the nature of reality itself. As observations become more precise and theoretical frameworks more sophisticated, we edge closer to breakthroughs that could revolutionize physics as profoundly as quantum mechanics and relativity did in the 20th century. The invisible universe that surrounds us holds secrets that might unlock new technologies, reveal the ultimate fate of the cosmos, and answer fundamental questions about why anything exists at all. The battle between dark matter and dark energy continues across scales and through time that dwarf human comprehension. Every galaxy we observe, every star that shines, every planet that harbors life represents a temporary victory of structure over dissolution in a cosmic war whose outcome will determine whether the universe ends in fire or ice. Understanding these invisible forces has become the defining challenge of modern physics, pushing the boundaries of human knowledge into territories that previous generations could never have imagined. The answers we seek might transform not only our understanding of the cosmos, but our conception of what it means to exist within a reality where the visible represents merely the surface of an infinite ocean of mystery. The invisible war between these cosmic titans has created casualties that challenge everything we thought we knew about the universe itself. Deep beneath the surface of our cosmic understanding, cracks are beginning to show. The most sophisticated measurements ever attempted are producing results that should be impossible according to our best theories. The precision instruments designed to solve these mysteries are instead revealing contradictions so fundamental that they threaten to topple the entire structure of modern cosmology. Consider what happens when scientists point the most advanced telescopes ever built toward the edge of the observable universe. They expect to see a cosmos that behaves according to mathematical laws refined over decades of careful observation. Instead, they discover galaxies that formed too early, structures that grew too quickly, and expansion rates that vary depending on how you measure them. Every new observation adds another piece to a puzzle that refuses to fit together according to the rules we thought governed reality. The cosmic microwave background radiation provides our most ancient view of the universe, captured when space first became transparent to light just 380,000 years after the Big Bang. This fossil radiation carries encoded information about cosmic conditions when the universe was barely 2% of its current age. The patterns frozen in this ancient light reveal the seeds that eventually grew into every galaxy cluster and cosmic void we observe today. But when scientists use this primordial blueprint to predict what the universe should look like now, their calculations consistently disagree with direct measurements of cosmic expansion. The early universe appears to have been expanding at one rate, while nearby observations indicate a completely different expansion speed. This discrepancy has persisted and grown stronger as measurements have become more precise, creating what cosmologists call the Hubble tension. The James Webb Space Telescope was humanity's billion-dollar attempt to resolve this crisis through the most precise distance measurements ever achieved. Its unprecedented infrared vision can peer through cosmic dust clouds that blind other instruments, revealing the true brightness of distant stars and galaxies. Every observation was expected to clarify the confusion surrounding cosmic expansion rates. Instead, Webb has confirmed that the disagreement is real and cannot be explained away by measurement errors. The implications cascade through every aspect of cosmology, like dominoes falling in slow motion. If the local expansion rate represents the true cosmic value, then the universe is younger than we calculated. This creates immediate conflicts with stellar ages that appear older than the cosmos itself. Ancient globular cluster stars would predate the Big Bang, violating the most fundamental constraint in physics that effects cannot precede their causes. Alternatively, if the cosmic microwave background predictions are correct, then something is systematically biasing our local measurements in ways we do not understand. Perhaps we occupy an unusual region of space where expansion rates differ from the cosmic average. Maybe dark energy behaves differently in different cosmic environments. Each possibility requires abandoning comfortable assumptions about the uniformity of physical law. The search for resolution has led scientists down increasingly exotic theoretical pathways that would have seemed like science fiction just decades ago. Early dark energy proposes that a mysterious force briefly accelerated cosmic expansion during the universe's first few 100,000 years before disappearing entirely. This hypothetical energy component would have given space an extra kick of expansion that could reconcile the conflicting measurements we observe today. The mathematics required to describe such early dark energy push theoretical physics into uncharted territory. The energy scales involved are so low that they cannot be reproduced in any terrestrial laboratory, yet they must have influenced cosmic evolution across billions of light years and billions of years of time. Understanding how such a force could emerge, dominate cosmic dynamics, and then vanish without a trace requires physics beyond anything in our current theoretical toolkit. Modified gravity theories offer an even more radical alternative by suggesting that Einstein's equations themselves break down on cosmic scales. These frameworks propose that gravitational attraction becomes stronger at large distances, or that additional dimensions of space affect how matter interacts across cosmic volumes. Such modifications could naturally explain apparent cosmic acceleration without requiring mysterious dark energy components. However, any modification to gravity must simultaneously explain the exquisite precision with which Einstein's theory describes everything from planetary orbits to gravitational wave detections. The mathematics become extraordinarily complex when attempting to create theories that behave like general relativity on small scales while producing different effects across cosmic distances. Most proposed modifications create new problems while solving old ones. The timescape model represents perhaps the most revolutionary alternative by questioning whether dark energy exists at all. This framework suggests that our measurements of cosmic acceleration result from systematic errors in how we calibrate time and distance across a universe filled with complex structure. Different regions of space might literally experience time at different rates due to gravitational effects, creating apparent acceleration without requiring any exotic energy components. According to timescape cosmology, clocks in dense galaxy clusters would run slower than identical clocks in empty cosmic voids due to gravitational time dilation. Over billions of years, these timing differences could accumulate to create systematic biases in how we measure distances and expansion rates. What appears to be cosmic acceleration might instead reflect our failure to account for the complex gravitational landscape through which light travels to reach our telescopes. Testing such radical alternatives requires observational precision that pushes current technology to its absolute limits. The Euclid space mission will map the positions and shapes of billions of galaxies with unprecedented accuracy, potentially distinguishing between different theoretical models through subtle patterns in how cosmic structure has evolved over time. These observations will probe whether Einstein's gravity correctly describes cosmic dynamics or whether alternative physics governs the largest scales in nature. Underground laboratories continue their relentless search for dark matter particles, using detection strategies that become more sophisticated with each passing year. The latest experiments operate in conditions so pristine that they can detect energy deposits equivalent to individual photons while rejecting background signals that might masquerade as dark matter interactions. These facilities represent some of the most sensitive scientific instruments ever constructed, capable of measuring effects that occur perhaps once per year in tons of target material. The failure to detect dark matter particles despite decades of increasingly sensitive searches has forced scientists to consider possibilities that seemed unlikely when the experiments began. Perhaps dark matter consists of particles so light that they barely interact with ordinary matter through any force except gravity. Axions represent this class of candidate particles, requiring completely different detection strategies based on their potential interactions with electromagnetic fields. The BRED experiment exemplifies this new generation of dark matter searches by abandoning the targeted approach of previous detectors in favor of broad surveys across thousands of potential particle masses simultaneously. Rather than focusing intensively on specific theoretical predictions, these experiments cast wide nets in hopes of catching dark matter particles whose properties might differ dramatically from theoretical expectations. Alternative explanations propose that dark matter might not consist of particles at all, but instead represent primordial black holes formed during the universe's earliest moments. These microscopic black holes would interact only gravitationally, explaining why particle detectors find nothing while still providing the invisible mass needed to explain galaxy rotation curves and gravitational lensing observations. Primordial black holes could have formed from extremely rare density fluctuations in the early universe that collapsed directly into black holes without ever becoming stars. These objects would be impossible to create today, but might have been common when the universe was hot and dense enough for quantum fluctuations to exceed the thresholds required for gravitational collapse. The theoretical landscape surrounding dark matter has become increasingly fragmented as experimental null results eliminate entire classes of candidate particles. Some models now propose that dark matter particles interact with each other through forces completely separate from the electromagnetic weak and strong forces that govern ordinary matter. This hidden sector physics could create rich dynamics invisible to conventional detectors. Self-interacting dark matter models suggest that dark matter particles can collide with each other, transferring energy and momentum in ways that alter how invisible matter accumulates in galaxy centers. These interactions would be far too weak to detect in laboratory experiments, but strong enough to affect cosmic structure formation over billions of years. Computer simulations incorporating such interactions produce galaxy properties that match observations more closely than simple collisionless dark matter models. The European Space Agency's Euclid mission, launched in 2023, represents humanity's most ambitious attempt to map the invisible universe through its gravitational effects on visible matter. This space telescope will observe billions of galaxies with precision sufficient to measure how their shapes have been distorted by gravitational lensing from intervening dark matter structures. The resulting maps will reveal dark matter distribution across cosmic scales and cosmic time with unprecedented detail. Euclid observations will also probe dark energy evolution by measuring baryon acoustic oscillations with extraordinary accuracy across different cosmic epochs. These fossil sound waves from the early universe provide standard rulers that reveal how cosmic expansion has changed over billions of years. Any deviation from constant dark energy should appear as systematic variations in how these standard rulers appear at different distances. The Nancy Grace Roman Space Telescope will extend these investigations even further through comprehensive surveys designed to discover thousands of supernovae and measure their properties with remarkable precision. These stellar explosions serve as standard candles that reveal cosmic distances and expansion rates across different periods in cosmic history. The combined observations will trace dark energy behavior with sensitivity sufficient to detect evolutionary changes smaller than 10%. Ground-based observatories are simultaneously pushing complementary detection strategies to new extremes of capability. The Vera Rubin Observatory will begin the most comprehensive survey of the night sky ever attempted, capturing images of the entire visible southern hemisphere every few nights for 10 years. This relentless monitoring will reveal how cosmic structure changes over time scales accessible to human observation. The observatory's unprecedented survey will discover millions of new galaxies, hundreds of thousands of supernovae, and countless other cosmic phenomena that will constrain dark matter and dark energy properties through statistical analyses of enormous datasets. Every night of observation will add thousands of new measurements to the growing body of evidence that either supports or challenges our theoretical understanding of invisible cosmic components. Extremely large telescopes currently under construction will have mirrors spanning 30 to 40 meters in diameter, collecting enough light to study individual stars in galaxies billions of light-years away. These observations will provide independent checks on cosmic distance measurements and expansion rates through techniques that avoid some of the systematic uncertainties affecting current observations. The combination of space-based precision and ground-based light-gathering power promises to resolve current tensions in cosmological measurements within the next decade. Either these observations will confirm that our understanding of dark matter and dark energy is essentially correct, or they will reveal systematic problems that require fundamental revisions to our theoretical frameworks. But perhaps the most profound challenge posed by dark matter and dark energy extends beyond their mysterious nature to questions about the limits of human knowledge itself. We have constructed our entire scientific worldview based on the 5% of cosmic reality that we can directly observe and manipulate in laboratory conditions. The remaining 95% operates according to rules that might be fundamentally alien to human intuition. This epistemological crisis forces us to confront uncomfortable questions about whether complete scientific understanding is achievable for phenomena that exist beyond direct observation. Dark matter particles might interact so weakly with ordinary matter that detecting them requires technologies we cannot yet imagine. Dark energy might operate through mechanisms so subtle that measuring them demands precision beyond what physics allows. The history of science offers both encouragement and caution about such challenges. Electromagnetic radiation was once as mysterious as dark energy appears today, yet it eventually yielded to theoretical understanding that enabled technologies from radio communication to medical imaging. Quantum mechanics emerged from puzzling observations that classical physics could not explain, ultimately revolutionizing our understanding of atomic and subatomic reality. These precedents suggest that today's cosmic mysteries might yield tomorrow's breakthrough insights that transform not only our understanding of the universe but our technological capabilities as well. Dark matter detection might require quantum sensors so sensitive that they enable entirely new forms of precision measurement. Dark energy research might reveal connections between cosmic acceleration and fundamental physics that open pathways to technologies we cannot currently conceive. Advanced civilizations elsewhere in the cosmos face identical challenges in understanding the invisible forces that dominate cosmic evolution. Dark matter and dark energy operate uniformly throughout the observable universe, creating the same puzzles for any intelligence capable of conducting precision astronomical observations. The solutions we discover might represent universal insights rather than parochial human perspectives limited by our particular evolutionary history. The search for these solutions has already pushed human knowledge into territories that previous generations could never have imagined. We routinely measure cosmic phenomena with precision that exceeds 1 part in 1,000 while probing energy scales that span more than 60 orders of magnitude from quantum mechanics to cosmology. These investigations represent some of the most challenging and sophisticated scientific endeavors in human history. Yet the questions we face grow more profound with every new observation. The invisible universe that dominates existence might operate according to principles so fundamentally different from our experience that our current mathematical frameworks prove inadequate to describe them. We might need conceptual revolutions as dramatic as those that gave us quantum mechanics and relativity to achieve genuine understanding of cosmic reality. The stakes extend far beyond academic curiosity to practical questions about humanity's cosmic future. Understanding dark energy evolution will determine whether we can predict the universe's ultimate fate and plan for civilizational survival across cosmic timescales. Dark matter detection might reveal new physics that enables technologies powerful enough to influence cosmic evolution itself. These investigations also connect to the deepest philosophical questions about existence and meaning. If the vast majority of cosmic reality remains forever beyond direct human perception, what does this imply about our significance in the cosmic scheme? Are we merely temporary patterns of organization in a universe dominated by forces we can never fully comprehend, or do we represent something unique and precious precisely because of our ability to contemplate these mysteries? The answers we seek might transform not only our understanding of dark matter and dark energy, but our conception of what it means to exist as conscious observers in a cosmos where the visible represents merely the surface of an infinite ocean of invisible reality. The battle between construction and destruction, between the forces that build cosmic structure and those that tear it apart, continues to unfold across scales and through time that dwarf human comprehension. Every measurement we make, every theory we construct, every experiment we conduct represents another move in our attempt to understand this cosmic chess game whose rules we are still discovering. The outcome will determine not only the fate of every star and galaxy, but the ultimate destiny of consciousness itself in a universe where the invisible holds dominion over everything we can see. The revelations emerging from our deepest cosmic investigations have shattered the comfortable illusion that we understand the universe we inhabit. As scientists peer further into space and time with instruments of unprecedented sensitivity, they discover not confirmation of established theories, but evidence of phenomena so bizarre that they challenge the very foundations of physical law. The invisible forces that dominate cosmic evolution appear to operate according to rules that exist beyond the boundaries of human comprehension. Recent observations from the most advanced space telescopes reveal galaxies that formed impossibly early in cosmic history, when the universe was supposedly too young and chaotic for such complex structures to exist. These ancient stellar cities blazed to life when space itself was barely 3% of its current age, defying every model of cosmic evolution that physicists have constructed over decades of careful research. The mathematics simply do not work. The time available for structure formation falls short by billions of years. Yet there they are, captured in exquisite detail by infrared sensors that can detect the faintest whispers of ancient starlight. These primordial galaxies contain billions of stars arranged in spiral arms and central bulges that should have required eons to develop through gravitational processes. Their very existence suggests that the early universe operated under physical conditions dramatically different from anything we observe today. The chemical composition of these ancient systems presents an equally baffling puzzle. Spectroscopic analysis reveals the presence of heavy elements like oxygen, carbon, and iron that can only be forged in the nuclear furnaces of massive stars. But creating these elements requires multiple generations of stellar evolution, with each generation living out its entire existence before exploding in supernovae that scatter heavy elements into space for incorporation into subsequent stellar populations. This cosmic recycling process should take hundreds of millions of years at minimum. The most massive stars burn through their nuclear fuel in just a few million years, but even they require time to form from collapsing gas clouds. The mathematics of stellar nucleosynthesis sets absolute limits on how quickly heavy elements can accumulate in any cosmic environment. These limits appear to have been violated on a massive scale throughout the early universe. The implications ripple through every aspect of our understanding of cosmic evolution. If galaxies could form this rapidly, then the invisible scaffolding of dark matter must have clumped together far more efficiently than current theories predict. The cosmic web of filaments and voids that guide structure formation on the largest scales might have emerged from quantum fluctuations through mechanisms we have never identified. Alternative explanations venture into even more exotic territory. Perhaps the fundamental constants of nature themselves were different in the early universe, allowing stars to burn through their life cycles at accelerated rates. Maybe gravity was stronger in the past, enabling rapid collapse of gas clouds into stellar nurseries. Such possibilities would require abandoning the assumption that physical laws remain constant across cosmic time and space. The detection of supermassive black holes in these ancient galaxies compounds the mystery exponentially. These cosmic monsters contain millions or billions of times the mass of our Sun, yet they existed when the universe was barely old enough for the first stars to ignite. Traditional black hole formation requires the death of massive stars, which must first live out their nuclear burning phases before collapsing into stellar remnants that can grow through accretion. Even under the most favorable conditions, this growth process should take hundreds of millions of years to produce black holes massive enough to influence entire galaxies. The discovery of fully mature supermassive black holes in the cosmic dawn suggests either unknown formation mechanisms or physics that operates on fundamentally different timescales than our models assume. Some theoretical frameworks propose that these black holes formed directly from the collapse of massive gas clouds during the universe's first few million years, bypassing the stellar formation phase entirely. Such primordial black holes would have emerged from density fluctuations so extreme that they exceed the statistical predictions of cosmic inflation by enormous factors. Their existence would indicate that the early universe contained far more structure and complexity than our theories accommodate. The energy output from these ancient black holes presents another layer of impossibility. When matter falls into a black hole, it releases tremendous amounts of radiation as gravitational forces heat the infalling material to millions of degrees. This process should limit how quickly black holes can grow by blowing away nearby gas that might otherwise feed their expansion. The luminous quasars powered by these feeding supermassive black holes should have regulated their own growth through radiation pressure. Yet observations reveal black holes that appear to have grown far faster than this self-regulation mechanism should allow. They consumed matter at rates that exceed theoretical limits by factors of 10 or more, achieving massive status through processes that remain completely mysterious. Their rapid growth might indicate unknown physics governing matter behavior in extreme gravitational fields. The cosmic timeline becomes even more problematic when scientists attempt to trace the formation of the first stars themselves. Population 3 stars, as they are called, should have been massive, short-lived giants composed almost entirely of hydrogen and helium from the Big Bang. These primordial suns would have burned furiously for just a few million years before exploding in hypernovae that scattered the first heavy elements across space. Computer simulations consistently show that forming these first stars should have been an incredibly difficult and slow process. The primordial gas clouds lacked the heavy elements that normally help gas cool and collapse under gravity. Without efficient cooling mechanisms, the gas should have remained hot and diffuse, resisting the gravitational collapse needed for star formation. The mathematics predict that the first stars should not have appeared until the universe was at least 100 million years old. Instead, observations suggest that massive star formation began almost immediately after the cosmic dark ages ended. The universe transitioned from complete darkness to active stellar production in what appears to be a cosmic eye blink. This acceleration of cosmic evolution by hundreds of millions of years demands explanations that push theoretical physics into uncharted territory. The chemical evolution problem extends beyond simple timing issues to questions about the efficiency of element production and distribution. Even if the first stars formed earlier than expected, they would need to produce heavy elements at rates far exceeding normal stellar nucleosynthesis to explain the chemical abundances observed in ancient galaxies. The nuclear reactions inside stars operate according to well-understood quantum mechanics that sets firm limits on element production rates. Some models propose that the first generation of stars was far more massive than anything that forms today, reaching sizes of hundreds or even thousands of solar masses. Such stellar giants would burn through their nuclear fuel at incredible rates, living for only hundreds of thousands of years before exploding in pair instability supernovae that completely destroy the star and scatter all its contents into space. These hypothetical supermassive stars could potentially explain both the rapid chemical enrichment and the early formation of seed black holes that grew into the supermassive monsters observed in ancient galaxies. However, no such stars exist in the modern universe, and the conditions required for their formation remain highly speculative. The physics governing such extreme stellar objects pushes beyond the boundaries of established stellar evolution theory. The observational evidence continues mounting from multiple independent sources, each confirming aspects of this impossible early cosmic evolution. Radio telescope observations detect molecular hydrogen in galaxies that formed when the universe was less than 1 billion years old. This simple molecule serves as the raw material for star formation, and its presence indicates that complex chemistry was already operating in the cosmic dawn. Gravitational lensing observations use the bending of spacetime by massive galaxy clusters to magnify and study even more distant objects. These cosmic telescopes reveal faint galaxies at distances that correspond to when the universe was just 400 million years old. The sheer number of galaxies detected at such distances suggests that star formation was proceeding at prodigious rates throughout the early cosmos. The statistical distribution of galaxy masses and brightness levels in the early universe deviates significantly from theoretical predictions. Computer simulations based on our best understanding of dark matter and cosmic structure formation consistently produce fewer bright galaxies at early times than observations reveal. The discrepancy suggests either fundamental gaps in our theoretical models or systematic biases in observational techniques that remain unidentified despite decades of refinement. Infrared observations penetrate the dust clouds that often obscure star formation regions, revealing the true rates at which ancient galaxies were converting gas into stars. These measurements indicate star formation rates that exceed modern galaxies by factors of 10 to 100. Such vigorous stellar production should have exhausted available gas supplies within a few 100 million years, yet many of these galaxies show evidence of sustained star formation over much longer periods. The dust itself presents another puzzle that compounds the mystery of accelerated cosmic evolution. Cosmic dust grains form primarily in the atmospheres of evolved stars that have progressed through multiple stages of nuclear burning. These particles consist of silicates, carbon compounds, and other heavy elements that condense from stellar winds as aging stars shed their outer layers. The presence of significant dust quantities in galaxies that formed when the universe was less than 1 billion years old indicates that multiple generations of stellar evolution had already occurred. This dust formation process should require hundreds of millions of years under any reasonable model of stellar physics, yet infrared telescopes detect substantial dust masses in some of the earliest galaxies ever observed. Alternative dust formation mechanisms have been proposed to explain this temporal impossibility. Perhaps dust grains formed directly from the explosive deaths of the first massive stars, condensing from supernova ejecta under conditions unlike anything in the modern universe. Or maybe primordial dust survived from even earlier epochs, forming during the first moments after the Big Bang through processes we have never identified. Each proposed solution to these timing problems requires invoking physics beyond our current theoretical frameworks. The early universe appears to have operated according to rules that differ fundamentally from the cosmic evolution we observe today. Whether these differences reflect unknown physical processes or systematic errors in our interpretation of ancient light remains hotly debated among cosmologists. The philosophical implications extend far beyond technical disputes about galaxy formation models. If the early universe could violate the timing constraints that govern modern cosmic evolution, then our understanding of physical law itself might be incomplete. The constants and equations that describe particle interactions, stellar physics, and gravitational dynamics might represent only local approximations to more complex underlying principles. This possibility challenges one of the most fundamental assumptions in physics, that natural laws remain constant across time and space. The success of physics as a predictive science depends critically on the reliability of mathematical relationships derived from local experiments and observations. If these relationships break down under the extreme conditions of the early universe, then our entire scientific methodology faces conceptual challenges. The accelerated pace of early cosmic evolution also raises questions about the role of consciousness and observation in determining physical outcomes. Some interpretations of quantum mechanics suggest that measurement and observation play active roles in determining the properties of physical systems. If consciousness emerged earlier in cosmic history than previously thought, it might have influenced the development of cosmic structure through mechanisms we do not understand. Advanced civilizations that developed in the early universe might have possessed technologies capable of manipulating cosmic evolution directly. Hypothetical megascale engineering projects could have accelerated star formation, enhanced chemical element production, or guided the growth of supermassive black holes through means that leave no obvious signatures detectable by modern astronomy. Such speculative possibilities highlight how much we still do not know about the universe we inhabit. The visible cosmos that inspired human curiosity throughout history represents only the outermost layer of a reality whose deeper structures remain largely hidden. Every new observation reveals additional complexities that challenge our theoretical understanding and push the boundaries of human knowledge. The technologies required to probe these mysteries continue advancing at remarkable rates, driven by the recognition that understanding dark matter and dark energy represents one of the greatest challenges in the history of science. Space-based observatories operating beyond Earth's atmosphere can detect wavelengths of light that never penetrate our planet's atmospheric shield, revealing cosmic phenomena invisible to ground-based instruments. Adaptive optics systems compensate for atmospheric turbulence in real time, allowing ground-based telescopes to achieve image quality that rivals space-based observations. These technologies enable astronomers to study individual stars in galaxies billions of light-years away, providing unprecedented detail about cosmic structure formation across vast distances and timescales. Interferometric techniques combine light from multiple telescopes separated by thousands of kilometers, creating virtual instruments with effective apertures larger than Earth itself. These arrays can measure stellar positions and motions with precision that approaches the fundamental limits imposed by quantum mechanics and general relativity. The computational resources required to analyze these observations have grown exponentially, demanding supercomputers capable of processing petabytes of data from systematic surveys of billions of cosmic objects. Machine learning algorithms trained on simulated datasets can identify subtle patterns in observational data that might escape human analysis, potentially revealing new classes of cosmic phenomena. Underground laboratories continue expanding their sensitivity to dark matter interactions through increasingly sophisticated shielding and detection strategies. The next generation of experiments will employ tons of target material operating at temperatures approaching absolute zero, creating conditions where even the faintest dark matter interactions might produce detectable signals. Quantum sensors based on principles of atomic interferometry and gravitational wave detection might eventually achieve sensitivity sufficient to detect dark matter through its gravitational effects on space-time itself. These technologies probe physics at the intersection of quantum mechanics and general relativity, potentially revealing connections between cosmic-scale phenomena and microscopic quantum processes. The convergence of observational astronomy, particle physics, and theoretical cosmology has created unprecedented opportunities for breakthrough discoveries that could revolutionize our understanding of reality itself. The invisible forces that dominate cosmic evolution operate according to principles we have barely begun to comprehend, challenging every assumption about the nature of space, time, matter, and energy. The battle between dark matter construction and dark energy destruction continues to unfold across scales that span from quantum fluctuations to cosmic horizons, shaping the destiny of every structure in the observable universe. Understanding this cosmic struggle has become the defining quest of modern physics, pushing human knowledge toward revelations that might transform not only our scientific worldview, but our conception of what it means to exist as conscious observers in a cosmos dominated by invisible forces. The answers we seek lie hidden within the fabric of space-time itself, encoded in gravitational waves that ripple across billions of light-years and quantum fields that fluctuate at energy scales beyond direct experimental access. Deciphering these cosmic messages requires technologies and theoretical frameworks that extend far beyond anything we possess today, demanding innovations that will challenge human ingenuity for generations to come. The quantum realm beneath visible reality harbors secrets that could unlock the cosmic mystery entirely. At energy scales so small they exist beyond the reach of any particle accelerator ever conceived, virtual particles flicker in and out of existence with such frequency that empty space itself seethes with invisible activity. This quantum foam might hold the key to understanding why dark energy behaves as it does, operating through mechanisms that connect the smallest possible scales to the largest structures in the universe. Theoretical calculations suggest that quantum field fluctuations in the vacuum should produce an energy density that dwarfs observed dark energy by more than 100 orders of magnitude. This represents the most catastrophic failure of prediction in the history of physics, indicating that our understanding of either quantum mechanics or general relativity contains fundamental errors. The resolution of this vacuum catastrophe might require revolutions in physics as profound as those that gave us quantum theory and relativity in the first place. Recent theoretical work has explored whether dark energy emerges from the collective behavior of quantum fields operating across cosmic volumes. These models propose that quantum entanglement between widely separated regions of space creates correlations that manifest as apparent cosmic acceleration. The mathematics describing such effects push beyond the boundaries of conventional field theory into territories where space and time themselves become emergent properties of more fundamental quantum processes. Alternative approaches suggest that dark energy represents a phase transition in the quantum vacuum itself, similar to how water transforms into ice steam when heated beyond a critical temperature. The universe might be evolving through a sequence of vacuum states, each characterized by different energy densities that drive expansion at different rates. Such phase transitions could explain why dark energy appears to be evolving over cosmic time rather than remaining constant. The search for these quantum signatures requires experimental precision that approaches the fundamental limits imposed by Heisenberg's uncertainty principle. Gravitational wave detectors like LIGO and Virgo have achieved sensitivity so extraordinary that they can measure distance changes smaller than 1/10,000th the width of a proton. These instruments detect ripples in space-time itself, potentially revealing how quantum effects influence cosmic geometry. Future gravitational wave observatories will extend this sensitivity across frequency ranges that probe different aspects of cosmic evolution. Space-based detectors will monitor gravitational waves with wavelengths spanning millions of kilometers, revealing phenomena invisible to ground-based instruments. These observations might detect the gravitational signatures of phase transitions in dark energy or quantum processes that shaped the early universe. The European Space Agency's LISA mission will create a gravitational wave detector with arms stretching 5 million kilometers through space, using laser interferometry to monitor the relative positions of free-floating test masses with unprecedented precision. This cosmic laboratory will probe gravitational phenomena across timescales ranging from seconds to billions of years, potentially revealing connections between quantum mechanics and cosmic evolution. Pulsar timing arrays represent another approach to gravitational wave astronomy, using the incredibly precise rotation periods of neutron stars as cosmic clocks to detect gravitational waves passing through our galactic neighborhood. These natural laboratories probe gravitational physics under conditions so extreme that matter approaches nuclear density while spinning hundreds of times per second. The quantum properties of dark matter particles remain equally mysterious, with theoretical predictions spanning energy scales from ultra-light axions to massive primordial black holes. Each possibility requires different experimental strategies and implies different connections to fundamental physics. Axion dark matter might interact with electromagnetic fields in ways that create detectable radio signals, while primordial black holes might evaporate through Hawking radiation at rates that depend on their initial masses. Laboratory experiments are pushing the boundaries of quantum measurement to probe these possibilities through increasingly sophisticated techniques. Atomic interferometers use quantum superposition to measure gravitational effects with sensitivity that exceeds classical instruments by orders of magnitude. These devices might eventually detect dark matter through its gravitational influence on atomic wave functions. Superconducting quantum interference devices operate at the boundary between classical and quantum physics, measuring magnetic fields with sensitivity that approaches fundamental quantum limits. Networks of these sensors distributed across the globe might detect dark matter interactions that create correlated signals spanning continental distances. The theoretical landscape connecting quantum mechanics to cosmic phenomena has expanded dramatically as physicists explore how microscopic processes might influence macroscopic evolution. Quantum field theory in curved spacetime predicts that gravitational fields can create and destroy particles through processes that have no analog in flat spacetime physics. These effects might explain how dark energy emerges from quantum vacuum fluctuations under specific cosmic conditions. Holographic principles suggest that all the information contained within any volume of space can be encoded on its boundary surface, implying deep connections between quantum information theory and gravitational physics. These ideas have led to proposals that space-time itself emerges from quantum entanglement patterns, with dark energy representing the energy cost of maintaining these quantum correlations across cosmic distances. String theory attempts to unify quantum mechanics with general relativity by proposing that fundamental particles are actually vibrating strings in higher dimensional space-time. These models naturally predict the existence of additional scalar fields that could behave like dark energy, providing mathematical frameworks for understanding cosmic acceleration through quantum processes. However, string theory makes predictions about energy scales so far beyond experimental reach that testing these ideas requires cosmic observations rather than laboratory experiments. Loop quantum gravity takes a different approach by proposing that spacetime itself has a discrete, quantized structure at the smallest scales. In this framework, the smooth geometry described by Einstein's equations emerges as an approximation valid only at scales much larger than the fundamental quantum units. Dark energy might represent corrections to classical gravity that become significant when averaged over cosmic volumes. These quantum gravity theories make specific predictions about how cosmic evolution should differ from classical general relativity. Some models predict that the Big Bang was actually a quantum bounce from a previous contracting phase, eliminating the initial singularity problem that plagues classical cosmology. Others suggest that time itself might be emergent from more fundamental quantum processes. Testing such radical possibilities requires observational strategies that probe the earliest moments of cosmic history with unprecedented precision. The cosmic microwave background radiation provides our most direct window into these primordial conditions, carrying information about quantum fluctuations that occurred when the universe was less than 1 second old. Subtle patterns in this ancient light might reveal signatures of quantum gravity effects or dark energy evolution. Future cosmic microwave background missions will map temperature and polarization fluctuations with sensitivity sufficient to detect quantum signatures from the universe's birth. These observations might reveal whether cosmic inflation was driven by quantum field dynamics, whether spacetime has a discrete structure, or whether dark energy was already operating during the universe's first moments. The Large Hadron Collider and future particle accelerators continue searching for new physics that might connect to dark matter and dark energy through high-energy collisions that recreate conditions from the early universe. These experiments probe energy scales where quantum effects dominate, potentially revealing particles or forces that influence cosmic evolution through mechanisms invisible at lower energies. Supersymmetry represents one theoretical framework that naturally provides dark matter candidates while connecting quantum mechanics to gravitational physics through mathematical symmetries that relate particles with different spin properties. If supersymmetric particles exist, they might be produced in high-energy collisions and detected through their decay products or missing energy signatures. Extra-dimensional theories suggest that our familiar three-dimensional space represents only a slice of a higher dimensional reality, where gravitational and quantum effects operate according to different rules. Dark matter and dark energy might represent phenomena that exist primarily in these extra dimensions, influencing our three-dimensional world through gravitational interactions that we interpret as mysterious invisible forces. Experimental tests of extra-dimensional theories require precision measurements of gravitational attraction at very short distances, where deviations from Newton's inverse square law might reveal the presence of additional spatial dimensions. These experiments probe gravitational physics at scales where quantum effects become important, potentially revealing connections between cosmic mysteries and fundamental quantum processes. The intersection of quantum mechanics and cosmology has revealed deep philosophical questions about the nature of physical reality that extend far beyond technical calculations. If quantum processes influence cosmic evolution, then the act of observation itself might play a role in determining cosmic outcomes through mechanisms we do not understand. The measurement problem in quantum mechanics, which asks how and when quantum superpositions collapse into definite states, becomes even more complex when applied to cosmic scale phenomena. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining physical outcomes, raising questions about whether intelligent observers influence cosmic evolution through their observations. If advanced civilizations exist throughout the universe, their collective observations might affect dark energy behavior or dark matter distribution through quantum measurement effects that operate across cosmic scales. The many worlds interpretation provides an alternative framework where all possible quantum outcomes occur simultaneously in parallel universes, eliminating the need for wave function collapse while implying that every possible cosmic evolution actually occurs. In this view, we observe one particular realization of cosmic evolution among infinite alternatives, with dark matter and dark energy representing just one possible solution to the cosmic structure formation problem. These quantum cosmological ideas push the boundaries of scientific knowledge into territories where physics, philosophy, and mathematics intersect in ways that challenge our most basic assumptions about the nature of reality. The invisible forces that dominate cosmic evolution might operate through quantum processes so fundamental that they precede the emergence of space and time themselves. Understanding these connections requires theoretical frameworks that extend far beyond current physics, demanding mathematical tools that can describe quantum processes operating across cosmic scales and time periods. The mathematics of quantum field theory in curved spacetime represents only the beginning of what might be needed to fully understand how quantum effects shape cosmic evolution. Computational approaches to these problems require supercomputers capable of simulating quantum processes across vast ranges of scale, from subatomic particles to cosmic structures. These simulations must account for quantum entanglement effects that might connect widely separated regions of space, creating correlations that influence cosmic evolution through mechanisms invisible to classical physics. Machine learning algorithms trained on quantum simulation data might identify patterns in cosmic structure that reveal quantum signatures invisible to human analysis. These artificial intelligence systems could potentially discover new connections between quantum mechanics and cosmic evolution by analyzing datasets too complex for traditional mathematical approaches. The convergence of quantum physics, cosmology, and advanced computation promises to revolutionize our understanding of the invisible universe within the coming decades. The quantum realm that underlies all physical reality might hold keys to unlocking the mysteries of dark matter and dark energy, revealing how the smallest scales in nature influence the largest structures in the cosmos. These investigations represent some of the most challenging and ambitious scientific endeavors in human history, pushing the boundaries of knowledge toward revelations that could transform not only our understanding of the universe but our conception of what it means to exist as quantum observers in a cosmos where consciousness itself might play a fundamental role in determining physical outcomes. The quantum foundations of cosmic reality remain largely hidden behind veils of mathematical complexity and experimental inaccessibility, yet each advance in theoretical understanding and observational capability brings us closer to breakthrough insights that might finally explain why the universe contains invisible forces so powerful that they control the destiny of every star, galaxy, and cosmic structure across all of space and time. The battle between quantum construction and cosmic destruction continues to unfold through mechanisms that operate simultaneously at the smallest and largest scales in nature. Understanding this multi-scale physics has become the ultimate frontier of human knowledge, demanding innovations in theory, experiment, and computation that will challenge our species' intellectual capabilities for generations to come. Every quantum fluctuation that occurred during the universe's first moments continues to influence cosmic evolution today through chains of cause and effect that span from microscopic to macroscopic scales. Deciphering these quantum signatures requires technologies and mathematical frameworks that extend far beyond anything we currently possess, representing challenges that will drive scientific progress toward revelations we can barely imagine. The invisible quantum substrate that underlies all physical reality holds secrets about dark matter, dark energy, and cosmic evolution that could unlock new technologies, reveal the ultimate fate of the universe, and answer fundamental questions about why quantum mechanics and general relativity describe a cosmos dominated by forces we cannot directly observe but cannot ignore. As our instruments become more sensitive and our theories more sophisticated, we edge closer to discovering whether the quantum realm provides the missing keys to understanding cosmic reality, or whether the mysteries of dark matter and dark energy require even more revolutionary insights that transcend our current conception of physics itself. The answers lie hidden within the fabric of space-time at scales so small they exist beyond direct observation, yet their effects shape cosmic destiny across distances and time periods that dwarf human comprehension. The mathematical architecture underlying cosmic reality operates through equations so complex that solving them requires computational resources that push against the fundamental limits of information processing. When physicists attempt to model how dark matter and dark energy interact across cosmic volumes containing billions of galaxies, the calculations demand supercomputers that consume enough electricity to power entire cities while running for months at a time. These simulations reveal disturbing patterns that suggest our universe balanced on the edge of mathematical chaos. Tiny changes in the initial conditions or fundamental constants produce dramatically different cosmic outcomes, indicating that the reality we observe represents just one possibility among infinite alternatives that could have emerged from the same physical laws. The numerical precision required to model cosmic evolution accurately stretches beyond what classical computers can achieve through conventional algorithms. Quantum computers might eventually provide the computational power necessary to simulate quantum field effects operating across cosmic scales, but such machines remain largely theoretical constructs that exist primarily in laboratory demonstrations rather than practical applications. Recent advances in artificial intelligence have begun revolutionizing how scientists analyze cosmic data by identifying patterns too subtle for human perception. Machine learning algorithms trained on simulated universes can distinguish between different dark energy models with accuracy that exceeds traditional statistical analysis. These artificial intelligence systems operate as cosmic detectives, sifting through petabytes of observational data to extract signals buried within noise levels that would overwhelm human researchers. Neural networks designed to recognize gravitational lensing signatures can process images from space telescopes faster than teams of graduate students, identifying distorted galaxy shapes that reveal dark matter distribution with precision that continues improving as the algorithms learn from larger datasets. The marriage of cosmic observation and artificial intelligence promises to accelerate discovery rates beyond what human analysis alone could achieve. But perhaps the most unsettling aspect of these computational investigations is what they reveal about the stability of cosmic structure itself. The mathematical models consistently show that galaxies, galaxy clusters, and the cosmic web exist in states of dynamic equilibrium that could be disrupted by relatively small perturbations in dark matter or dark energy behavior. Computer simulations that extend billions of years into the future reveal scenarios where slight changes in dark energy evolution could trigger cascade failures that unravel cosmic structure entirely. Galaxy clusters might disperse as dark energy overwhelms gravitational binding. The cosmic web could fragment as expansion rates accelerate beyond critical thresholds. Stars might be stripped from their host galaxies as space itself expands so rapidly that gravitational forces cannot maintain stable orbits. These computational prophecies depend critically on assumptions about how dark energy will behave over cosmic timescales that exceed human comprehension. If dark energy continues strengthening at its current rate, the universe faces a future where accelerating expansion eventually overcomes every force in nature, tearing apart molecules, atoms, and ultimately space-time itself in a catastrophic event known as the Big Rip. Alternative scenarios emerge when computational models incorporate different assumptions about dark energy evolution. If this mysterious force weakens over time, cosmic expansion might eventually halt and reverse, leading to a big crunch where every galaxy, star, and planet gets compressed back into the hot, dense state from which the universe originally emerged. Perhaps most intriguingly, some models suggest that dark energy evolution might be cyclical, strengthening and weakening over periods lasting hundreds of billions of years. Such oscillations could create a universe that expands and contracts repeatedly, with each cycle destroying existing structure while providing raw materials for new cosmic architecture to emerge from the ashes of the previous iteration. The mathematical frameworks describing these possibilities push theoretical physics into territories where conventional concepts of space and time break down entirely. The equations governing cosmic evolution under extreme conditions require mathematical tools that exist at the cutting edge of pure mathematics, demanding innovations in differential geometry, topology, and algebraic structures that challenge even the most sophisticated theorists. String theory calculations suggest that dark energy might emerge from interactions between our familiar three-dimensional space and additional dimensions that remain hidden at scales we cannot directly observe. The mathematics describing such higher dimensional physics requires techniques so advanced that only a few hundred researchers worldwide possess the expertise necessary to work with them effectively. Loop quantum gravity approaches the problem from an entirely different mathematical direction by proposing that spacetime itself has a discrete, granular structure at the smallest possible scales. The calculations required to understand how such quantized geometry affects cosmic evolution demand new mathematical frameworks that bridge quantum mechanics and general relativity through novel algebraic structures. Computational cosmology has revealed that our universe appears to exist within an incredibly narrow range of parameters that permit the formation of complex structure. Slight changes in the strength of dark energy, the density of dark matter, or the values of fundamental constants would produce cosmos where stars never form, galaxies never coalesce, or space expands so rapidly that matter never has the opportunity to organize into interesting configurations. This fine-tuning problem suggests either remarkable cosmic coincidence or underlying physical principles that naturally produce universes capable of supporting complex structure. Anthropic selection offers one possible explanation, arguing that we observe these particular parameter values only because universes with different values could not produce observers capable of measuring them. Multiverse theories provide an alternative framework where every possible combination of physical parameters actually occurs somewhere within an infinite ensemble of universes. In this view, our cosmos represents just one bubble in an infinite foam of realities, each operating according to different physical laws and containing different types of matter and energy. The mathematical description of such multiverse scenarios requires techniques from probability theory, measure theory, and infinite dimensional analysis that push beyond the boundaries of conventional physics. Calculating the likelihood of observing particular parameter values within an infinite multiverse raises profound questions about the meaning of probability itself when applied to infinite sets of possibilities. Computational approaches to these problems demand algorithms that can explore vast parameter spaces containing billions of possible universes while identifying the subset that produces conditions compatible with complex structure formation. Such calculations require computational resources that scale exponentially with the number of parameters being varied, quickly exceeding the capacity of any conceivable computer. Recent theoretical work has explored whether quantum computational techniques might provide more efficient approaches to these multiverse calculations. Quantum algorithms that exploit superposition and entanglement effects could potentially explore multiple parameter combinations simultaneously, providing exponential speedups for certain classes of cosmological calculations. But the fundamental challenge extends beyond computational limitations to deeper questions about whether mathematical models can ever fully capture the complexity of cosmic reality. The equations describing dark matter and dark energy interactions operate in regimes where quantum mechanics, general relativity, and thermodynamics all become relevant simultaneously, creating mathematical systems too complex for analytical solution. Numerical approaches to these equations require approximations and simplifications that might miss essential physics governing cosmic evolution. The computational grids used to discretize space and time necessarily introduce artificial boundaries and resolution limits that could affect the outcomes of simulations in subtle but important ways. Verification of computational results becomes extraordinarily difficult when the systems being modeled operate on scales far beyond direct experimental access. Unlike laboratory physics, where theoretical predictions can be tested through controlled experiments, cosmological models must be validated through observations of phenomena that occurred billions of years ago under conditions that cannot be reproduced. The statistical analysis of cosmic observations presents its own mathematical challenges that push beyond conventional data analysis techniques. When scientists attempt to measure dark energy evolution by analyzing thousands of supernovae observations, they must account for systematic errors that could masquerade as cosmic acceleration, selection biases that affect which objects get included in their samples, and correlations between different measurements that complicate traditional statistical inference. Bayesian analysis provides mathematical frameworks for incorporating prior knowledge and uncertainty quantification into cosmological parameter estimation, but these techniques require assumptions about probability distributions that might not accurately represent the true uncertainties in cosmic measurements. The choice of prior distributions can significantly influence the conclusions drawn from observational data, raising questions about the objectivity of scientific inference. Machine learning approaches offer alternative strategies for extracting information from cosmic datasets without making explicit assumptions about underlying probability distributions. These algorithms can identify patterns in observational data that might reveal signatures of dark energy evolution or dark matter interactions through purely empirical approaches that avoid some of the theoretical biases inherent in traditional analysis methods. However, machine learning systems trained on simulated data might miss phenomena that occur in the real universe but were not included in the training simulations. The algorithms could potentially discover spurious patterns that reflect computational artifacts rather than genuine physical effects, creating false discoveries that mislead scientific understanding. The validation of machine learning results in cosmology requires independent confirmation through multiple observational techniques and theoretical frameworks. This process becomes particularly challenging when the phenomena being studied operate on scales where direct experimental verification remains impossible for the foreseeable future. Advanced statistical techniques from information theory and complexity science offer new approaches to quantifying the amount of structure and organization present in cosmic observations. These methods can potentially distinguish between genuine signals of dark energy evolution and random fluctuations that might appear significant in small datasets. Network analysis techniques borrowed from social science and biology provide tools for understanding how galaxies and galaxy clusters organize into the cosmic web through gravitational interactions. These approaches reveal emergent properties of cosmic structure that might not be apparent from traditional astronomical analysis methods. The mathematical tools required to understand cosmic evolution continue expanding as physicists draw inspiration from diverse fields, including condensed matter physics, fluid dynamics, and even biology. Techniques originally developed to understand phase transitions in materials, science provide insights into how dark energy might undergo changes of state that affect its cosmic influence. Hydrodynamic simulations adapted from engineering applications help model how ordinary matter behaves in the extreme environments created by dark matter gravitational fields. These calculations reveal how gas flows through the cosmic web, potentially affecting star formation rates and galaxy evolution in ways that influence our observations of cosmic structure. The convergence of multiple mathematical disciplines around cosmic problems has created new interdisciplinary fields that bridge astronomy, physics, mathematics, and computer science. These collaborations produce theoretical insights that no single discipline could achieve independently, demonstrating how cosmic mysteries drive innovation across the entire spectrum of quantitative sciences. Yet despite these mathematical advances, the fundamental nature of dark matter and dark energy remains as mysterious as ever. The equations describe their effects with increasing precision, but the underlying physics that produces these effects continues to elude our theoretical understanding. Mathematics provides the language for describing cosmic phenomena, but it cannot by itself reveal the deeper principles that govern invisible forces we cannot directly observe. The mathematical description of cosmic evolution has become so complex that it challenges the limits of human comprehension. The equations governing dark matter and dark energy interactions across cosmic scales contain thousands of terms representing different physical effects, creating mathematical systems that no individual researcher can fully understand in their entirety. Collaborative research teams distributed across multiple institutions work together to tackle different aspects of these computational challenges, with each group contributing specialized expertise to problems that exceed what any single researcher could address independently. These collaborations represent new models of scientific investigation that might be necessary for understanding phenomena that operate beyond human-scale intuition. The mathematical legacy of dark matter and dark energy research extends far beyond cosmology to influence pure mathematics itself. The computational demands of cosmic simulations have driven advances in numerical analysis, parallel computing, and algorithm development that find applications across science and engineering. The mathematical tools developed for understanding invisible cosmic forces continue generating insights in fields ranging from climate modeling to financial analysis. As our mathematical sophistication continues growing, we edge closer to theoretical frameworks that might finally explain why the universe contains forces we cannot see but cannot ignore. The equations describing cosmic reality become more accurate with each passing year, but they also reveal new layers of complexity that demand even more advanced mathematical tools for their complete understanding. The mathematical journey into cosmic darkness has only just begun, with each computational breakthrough revealing new mathematical challenges that push the boundaries of human knowledge toward territories where numbers themselves might provide the keys to unlocking the deepest secrets of invisible reality. The mathematical symphony of cosmic evolution plays out through equations so intricate that they challenge the fundamental limits of computational physics itself. When researchers attempt to model how invisible forces shape galactic clusters across billions of years, their calculations require numerical methods that push supercomputers beyond conventional algorithmic approaches into territories where quantum computational principles might offer the only viable solutions. These computational investigations reveal something deeply unsettling about the mathematical foundations underlying cosmic reality. The equations governing dark matter distribution and dark energy evolution contain non-linear terms that amplify tiny uncertainties into dramatically different outcomes, suggesting that predicting cosmic futures with absolute certainty might be mathematically impossible regardless of how precisely we measure initial conditions. Chaos theory provides mathematical frameworks for understanding how deterministic systems can produce unpredictable behavior through sensitive dependence on initial conditions. Applied to cosmic evolution, these principles suggest that the universe itself might operate as a chaotic system where microscopic quantum fluctuations during the first moments after creation continue influencing galactic dynamics across cosmic time through butterfly effect amplification. The mathematical description of this cosmic chaos requires techniques from dynamical systems theory that operate at the intersection of differential geometry and probability theory. These hybrid mathematical frameworks attempt to quantify uncertainty propagation through systems so complex that traditional analytical methods fail entirely, demanding numerical approaches that consume computational resources at rates that scale exponentially with system complexity. Strange attractors emerge from the mathematical analysis of cosmic structure formation, revealing hidden patterns in how matter organizes itself under the competing influences of gravitational attraction and dark energy repulsion. These mathematical objects exist in phase spaces with thousands of dimensions, representing cosmic states that evolve according to equations too complex for human visualization, but accessible through computational exploration. The fractal geometry underlying cosmic structure distribution provides another mathematical lens through which to understand how invisible forces create patterns that repeat across multiple scales. Galaxy clusters, superclusters, and cosmic voids organize themselves according to mathematical principles that echo the self-similar structures found throughout nature, from snowflakes to coastlines to the branching patterns of river systems. Computational fluid dynamics simulations reveal how ordinary matter flows through the invisible scaffolding provided by dark matter gravitational fields, creating turbulent patterns that influence star formation rates across cosmic time. These hydrodynamic calculations operate in regimes where quantum effects, relativistic corrections, and thermodynamic processes all contribute simultaneously to outcomes that determine galactic evolution. The mathematical treatment of such multi-physics systems requires numerical methods that can handle disparate timescales ranging from quantum to classical to relativistic processes occurring in femtoseconds to cosmic evolution unfolding over billions of years. Adaptive mesh refinement techniques allow simulations to focus computational resources on regions where rapid changes occur while maintaining broader context across vast spatial scales. Machine learning algorithms trained on these multi-scale simulations have begun discovering mathematical relationships that human researchers had not previously recognized. Neural networks can identify subtle correlations between dark matter halo properties and galaxy formation rates that emerge from complex interactions too intricate for traditional statistical analysis to detect. These artificial intelligence discoveries suggest that cosmic evolution follows mathematical patterns more sophisticated than current theoretical frameworks accommodate. The algorithms reveal emergent behaviors in cosmic structure formation that arise from collective interactions between billions of individual components, creating macroscopic phenomena that cannot be predicted from microscopic physics alone. Network theory provides mathematical tools for analyzing these emergent properties by representing cosmic structure as graphs where galaxies serve as nodes connected by edges representing gravitational interactions. The topology of these cosmic networks reveals organizational principles that might reflect fundamental properties of how matter self-organizes under the influence of invisible forces. Small world network phenomena appear throughout cosmic structure, where most galaxies remain connected through relatively short chains of gravitational interactions, despite the vast distances separating them. This mathematical property emerges naturally from dark matter distribution patterns, suggesting deep connections between network topology and invisible matter physics. Scale-free network characteristics manifest in galaxy cluster hierarchies, where the probability of finding clusters with specific masses follows power law distributions that remain invariant across different cosmic epochs. These mathematical scaling relationships provide clues about the underlying processes that govern structure formation through mechanisms we cannot directly observe. The mathematical description of cosmic network evolution requires techniques from algebraic topology that can track how connectivity patterns change as space expands and dark energy influences strengthen over time. These calculations reveal critical transitions where cosmic network properties undergo sudden changes that affect how information and matter flow through the universe. Information theory provides quantitative measures of cosmic organization by calculating the entropy content of galaxy distributions and structure formation patterns. These calculations reveal that the universe maintains remarkably low entropy states despite operating under physical processes that should increase disorder according to thermodynamic principles. The mathematical resolution of this cosmic entropy paradox might require extensions to classical thermodynamics that account for gravitational effects operating across cosmic scales. Gravitational entropy calculations suggest that space-time curvature itself contributes to cosmic organization in ways that classical thermodynamic analysis cannot capture. Quantum information theory offers alternative approaches to understanding cosmic organization by treating the universe as a vast quantum computer where cosmic structure formation represents computational processes operating through quantum field interactions. These frameworks suggest that dark energy and dark matter might represent computational resources that the universe uses to process information about its own evolution. The mathematical complexity of quantum information processing across cosmic scales exceeds anything achievable with classical computational models. Quantum entanglement between widely separated regions of space could create correlations that influence cosmic evolution through mechanisms that operate faster than light speed limitations would normally allow. Topological quantum field theories provide mathematical frameworks for describing how quantum information might propagate through space-time in ways that affect macroscopic cosmic evolution. These theories predict that cosmic structure formation could be influenced by quantum computational processes that operate according to mathematical principles completely different from classical physics. The mathematical verification of such quantum cosmological effects requires observational strategies that can detect quantum signatures in cosmic structure patterns. Statistical analysis of galaxy correlation functions might reveal quantum entanglement effects that manifest as subtle deviations from classical gravitational clustering predictions. Computational complexity theory provides mathematical bounds on how much information processing the universe can perform using its available matter and energy resources. These calculations suggest that cosmic structure formation might represent optimization processes that maximize information processing capacity while minimizing energy expenditure. The mathematical optimization principles underlying cosmic evolution might explain why dark energy and dark matter exist in the precise proportions needed to create maximum structural complexity. universe configurations with different invisible force ratios would produce less complex outcomes that contain fewer opportunities for information processing and organization. Game theory applications to cosmic evolution explore how different regions of space might compete for matter and energy resources under constraints imposed by dark energy expansion. These mathematical models reveal Nash equilibrium solutions where cosmic structure formation achieves stable configurations that balance competing gravitational and expansion forces. Evolutionary algorithms inspired by biological natural selection provide computational approaches to understanding how cosmic structure evolves toward increasingly complex configurations over time. These mathematical frameworks suggest that cosmic evolution follows optimization principles similar to those governing biological adaptation. The mathematical description of cosmic evolution as an optimization process requires objective functions that quantify cosmic fitness in terms of structural complexity, information processing capacity, and long-term stability. These calculations reveal that observable cosmic structure might represent solutions to mathematical optimization problems operating across scales from quantum to cosmic. Variational principles from classical mechanics extend to cosmic scales through mathematical frameworks that describe cosmic evolution as following paths through configuration space that extremize action integrals. These mathematical principles suggest that dark energy and dark matter behavior might emerge from fundamental optimization principles built into the mathematical structure of space-time itself. The calculus of variations applied to cosmic evolution produces field equations that generalize Einstein's general relativity to include additional terms representing dark energy and dark matter effects. These extended mathematical frameworks predict cosmic behavior that matches observations while providing deeper theoretical understanding of why invisible forces exist. Differential geometry on infinite-dimensional manifolds provides mathematical tools for describing cosmic evolution as motion through abstract spaces where each point represents a complete cosmic configuration. The mathematical analysis of geodesics in these spaces reveals optimal paths that cosmic evolution follows under the influence of invisible forces. Fiber bundle mathematics describes how local physics connects to global cosmic properties through mathematical structures that encode relationships between microscopic quantum processes and macroscopic cosmic evolution. These mathematical frameworks suggest that dark matter and dark energy represent different aspects of unified geometric principles. Algebraic geometry provides tools for analyzing the mathematical constraints that limit possible cosmic evolution pathways. These techniques reveal that observable cosmic structure exists within restricted regions of parameter space defined by mathematical relationships between fundamental constants and cosmic evolution equations. The mathematical landscape of possible cosmic configurations contains vast regions where different combinations of dark energy and dark matter properties would produce universes with dramatically different structural outcomes. Our observed cosmic configuration appears to exist at special locations within this mathematical landscape where complex structure formation becomes possible. Catastrophe theory provides mathematical frameworks for understanding how small changes in invisible force properties could trigger sudden transitions to completely different cosmic evolution pathways. These mathematical models reveal critical points where cosmic evolution becomes unstable and sensitive to perturbations that might fundamentally alter universal destiny. The mathematical analysis of cosmic stability requires techniques from bifurcation theory that can identify parameter ranges where cosmic evolution undergoes qualitative changes in behavior. These calculations reveal that our universe might exist close to mathematical boundaries where slight changes in dark energy evolution could trigger transitions to expansion modes that prevent further structure formation. Morse theory applications to cosmic evolution identify critical points in the mathematical landscape where cosmic development changes direction or encounters barriers that affect long-term outcomes. These mathematical techniques reveal that cosmic evolution might follow predetermined pathways through abstract mathematical spaces that determine universal fate. The mathematical beauty underlying cosmic evolution emerges through symmetry principles that connect abstract mathematical structures to physical processes operating across cosmic scales. These symmetries suggest that dark energy and dark matter represent manifestations of deeper mathematical principles that govern how reality organizes itself through mechanisms we have barely begun to understand. Group theory applications to cosmic evolution reveal mathematical symmetries that remain invariant despite the complex interactions between visible matter, and dark energy across cosmic time. These symmetrical relationships provide mathematical constraints that limit possible cosmic evolution pathways, while suggesting connections to fundamental mathematical principles. Representation theory provides mathematical tools for understanding how these cosmic symmetries manifest in observable phenomena through transformations that connect different mathematical descriptions of the same physical processes. These mathematical frameworks reveal hidden connections between apparently different aspects of cosmic evolution. The mathematical journey into cosmic darkness continues advancing through increasingly sophisticated theoretical frameworks that push the boundaries of human mathematical understanding toward territories where numbers and equations might finally reveal the ultimate nature of invisible forces that control cosmic destiny across all scales of space and time. Each mathematical breakthrough brings us closer to theoretical insights that could revolutionize our understanding of why the universe operates according to principles we can describe with extraordinary precision, but cannot yet explain through more fundamental physical reasoning. The mathematical descriptions become more accurate and comprehensive with each advancing year, yet they also reveal new layers of mathematical complexity that demand even more sophisticated tools for their complete understanding. The mathematical architecture underlying cosmic reality operates through principles so profound that understanding them fully might require mathematical innovations as revolutionary as calculus, complex analysis, or differential geometry were in their historical contexts. The invisible forces shaping cosmic evolution continue challenging human mathematical capabilities while promising revelations that could transform not only our understanding of the universe, but mathematics itself. The mathematical revelations emerging from our deepest cosmic investigations have exposed fractures in reality so profound they threaten to collapse our entire understanding of physical law. As scientists deploy increasingly sophisticated instruments to probe the invisible forces governing cosmic evolution, they discover not elegant confirmation of theoretical predictions, but evidence of phenomena so alien that they operate beyond the conceptual boundaries of human comprehension. Recent observations from gravitational wave observatories have detected ripples in spacetime that carry signatures inconsistent with any known cosmic process. These disturbances propagate through the fabric of reality itself at velocities that should be impossible, creating interference patterns that suggest multiple sources operating simultaneously across dimensions we cannot perceive directly. The mathematical analysis of these signals requires computational frameworks that push beyond conventional differential geometry into territories where spacetime itself becomes a dynamic, evolving entity. The precision required to interpret these gravitational whispers demands measurement capabilities that approach the fundamental limits imposed by quantum mechanics. Scientists have constructed interferometers so sensitive they can detect distance changes smaller than 1/10,000th the width of a proton, while filtering out vibrations from earthquakes occurring on the opposite side of the planet. These instruments operate at the boundary between classical measurement and quantum uncertainty, revealing cosmic phenomena that exist in regimes where traditional physics concepts break down entirely. Underground laboratories buried beneath miles of solid rock continue their relentless search for dark matter interactions using detection strategies that become more exotic with each passing year. Liquid xenon targets cooled to temperatures approaching absolute zero await collisions with hypothetical particles that might occur perhaps once in a decade, despite billions of potential interactions every second. The absence of confirmed detections has forced researchers to consider possibilities that challenge the most basic assumptions about particle physics and cosmic evolution. Axion detection experiments represent the cutting edge of this technological frontier, using superconducting cavities and powerful magnetic fields to search for ghostly particles so weakly interacting they could pass through light years of solid matter without leaving a trace. These devices scan across thousands of potential particle masses simultaneously, abandoning the focused strategies of previous searches in favor of comprehensive surveys that might catch dark matter candidates whose properties differ dramatically from theoretical expectations. The statistical analysis of null results from these experiments has begun revealing patterns that suggest dark matter might not consist of particles at all. Alternative explanations invoke modifications to gravitational physics that become significant only at cosmic scales, creating apparent dark matter effects without requiring any new particles. These modified gravity theories predict specific signatures in cosmic structure formation that future observations should be able to distinguish from particle dark matter models. However, the most disturbing aspect of these investigations is not their failure to detect expected phenomena, but their success in revealing unexpected ones. Cosmic ray observatories monitoring the highest energy particles in the universe have detected events that exceed theoretical energy limits by orders of magnitude. These ultra-high energy cosmic rays carry energies equivalent to professionally pitched baseballs compressed into subatomic particles. Yet no known astrophysical process can accelerate particles to such extreme velocities. The origin of these cosmic bullets remains completely mysterious despite decades of investigation using the most sensitive particle detectors ever constructed. Their arrival directions show no correlation with known cosmic accelerators like supernova remnants or active galactic nuclei. They appear to emerge from empty regions of space where no energetic phenomena should exist, suggesting unknown cosmic mechanisms operating through processes we have never identified. Neutrino astronomy has opened another window into cosmic mysteries by detecting nearly massless particles that travel at light speed while interacting so weakly with matter that they can traverse entire planets without deviation. IceCube and other neutrino observatories have mapped the high-energy neutrino sky, revealing cosmic accelerators that remain invisible to conventional telescopes. These observations suggest that the universe contains far more violent processes than visible light astronomy has ever revealed. The mathematical frameworks required to interpret neutrino observations push particle physics into regimes where quantum field theory intersects with general relativity through mechanisms that remain poorly understood. Neutrino oscillations indicate that these particles have tiny but non-zero masses that require extensions to the standard model of particle physics. The cosmic implications of neutrino mass remain unclear, but they might contribute to dark matter density or influence cosmic structure formation through subtle gravitational effects. Precision measurements of cosmic expansion using Type Ia supernovae continue revealing systematic deviations from simple dark energy models that grow more significant as observations become more accurate. The Hubble tension persists despite technological advances that have reduced measurement uncertainties to unprecedented levels. Multiple independent observational techniques consistently produce conflicting results that cannot be reconciled within existing theoretical frameworks. The statistical significance of these discrepancies has reached levels that demand serious consideration of revolutionary alternatives to standard cosmology. Early dark energy models propose that cosmic acceleration began much earlier than previously thought, operating through mechanisms that influence structure formation during the universe's first few 100 million years. These theories predict specific patterns in cosmic microwave background radiation and galaxy clustering that future observations should be able to confirm or eliminate. Alternatively, the timescape model suggests that our measurements of cosmic acceleration result from systematic errors in how we account for the complex gravitational landscape through which light travels to reach our telescopes. Different regions of space might experience time at different rates due to varying gravitational potentials, creating apparent acceleration without requiring any exotic energy components. This framework predicts that precision measurements across cosmic distances should reveal timing variations that correlate with matter density along different lines of sight. Testing such radical alternatives requires observational campaigns that span decades while maintaining unprecedented calibration accuracy across multiple independent measurement techniques. The European Space Agency's Euclid mission and NASA's upcoming Roman Space Telescope represent humanity's most ambitious attempts to map cosmic structure with sufficient precision to distinguish between competing theoretical models through statistical analysis of billions of galaxy observations. These space-based observatories will measure gravitational lensing effects with accuracy sufficient to reveal how dark matter distribution has evolved over cosmic time. The subtle distortions in galaxy shapes caused by intervening dark matter create statistical patterns that encode information about cosmic expansion history and structure formation processes. Analyzing these patterns requires computational algorithms that can extract signals buried within noise levels that would overwhelm traditional statistical approaches. Machine learning techniques trained on simulated cosmic datasets have revolutionized how scientists analyze observational data by identifying correlations too subtle for human perception. Neural networks can process images from space telescopes faster than teams of researchers while detecting lensing signatures with accuracy that improves continuously as the algorithms learn from larger training datasets. These artificial intelligence systems represent cosmic archaeologists that sift through petabytes of data searching for patterns that reveal the invisible architecture underlying cosmic structure. The convergence of space-based observation and artificial intelligence promises to accelerate cosmic discovery beyond what human analysis could achieve independently. Automated systems can monitor thousands of supernovae simultaneously while tracking their brightness evolution with precision sufficient to detect variations in dark energy behavior across different cosmic epochs. These observations might finally resolve whether dark energy represents a cosmological constant or an evolving field that changes over cosmic time. However, the most profound challenge facing cosmology extends beyond measurement precision to questions about the fundamental nature of scientific knowledge itself. The invisible forces dominating cosmic evolution operate through mechanisms so alien to human experience that our evolved cognitive architecture might lack the conceptual frameworks necessary to achieve complete understanding. We might represent biological intelligence attempting to comprehend phenomena that require forms of reasoning as foreign to human thought as quantum mechanics was to classical intuition. The mathematical description of cosmic evolution has become so complex that no individual researcher can fully comprehend the theoretical frameworks in their entirety. Collaborative teams distributed across multiple institutions work together on problems that exceed what any single human mind could address independently. These research collaborations represent new models of scientific investigation that might be necessary for understanding phenomena operating beyond human-scale intuition. Advanced civilizations elsewhere in the cosmos face identical challenges in understanding dark matter and dark energy, since these forces operate uniformly throughout the observable universe. The solutions we discover might represent universal insights rather than parochial perspectives limited by human evolutionary history. Alternative forms of intelligence might approach these problems through cognitive strategies completely different from human mathematical reasoning. The search for cosmic understanding has already pushed human knowledge into territories that previous generations could never have imagined. We routinely measure phenomena with precision that approaches fundamental quantum limits, while modeling systems that span 60 orders of magnitude in scale from particle physics to cosmic structure formation. These investigations represent some of the most sophisticated intellectual achievements in human history. Yet the questions we face grow more profound with every new observation. The universe reveals layers of complexity that demand increasingly radical departures from comfortable theoretical assumptions. Each breakthrough in observational capability exposes new mysteries that challenge our most basic beliefs about the nature of reality itself. The invisible forces controlling cosmic destiny operate through principles so strange that understanding them might require abandoning human-centered concepts of space, time, matter, and causation. The technological capabilities required to probe these mysteries continue advancing at exponential rates, driven by recognition that cosmic understanding represents the ultimate intellectual frontier. Quantum sensors based on atomic interferometry achieve sensitivity that rivals gravitational wave detectors while probing different aspects of space-time curvature. These devices might eventually detect dark matter through its gravitational effects on quantum systems rather than through direct particle interactions. Space-based gravitational wave observatories will extend detection capabilities across frequency ranges that probe cosmic phenomena invisible to ground-based instruments. The laser interferometer space antenna will create a detector with arms spanning millions of kilometers, monitoring gravitational waves from cosmic sources that operated when the universe was young. These observations might reveal whether dark energy evolution correlates with gravitational wave production through mechanisms we have never considered. Pulsar timing arrays use neutron stars as cosmic clocks to detect gravitational waves passing through our galactic neighborhood. These natural laboratories probe gravitational physics under conditions so extreme that matter approaches nuclear density while spinning hundreds of times per second. The timing precision achieved by monitoring multiple pulsars simultaneously exceeds what any artificial clock could provide, creating opportunities to test general relativity in regimes where quantum effects might influence gravitational dynamics. The theoretical implications of these observations extend far beyond confirming existing models to potentially revealing new physics that connects quantum mechanics with cosmic evolution through mechanisms operating across all scales simultaneously. The invisible universe surrounding us might represent manifestations of quantum processes so fundamental that they precede the emergence of classical space-time geometry. Understanding these connections requires mathematical frameworks that bridge quantum field theory and general relativity through novel approaches that abandon traditional assumptions about the separability of microscopic and macroscopic physics. The search for quantum signatures in cosmic structure formation has become one of the most challenging frontiers in theoretical physics, demanding innovations that could revolutionize our understanding of reality itself. The stakes could not be higher. Deciphering the nature of dark matter and dark energy will determine whether we can predict cosmic destiny, achieve technological capabilities that influence cosmic evolution, and answer fundamental questions about why conscious observers exist in a universe dominated by invisible forces. The answers we seek might transform not only our scientific worldview, but our conception of what it means to exist as temporary patterns of organization in a cosmos where the visible represents merely surface phenomena, obscuring deeper layers of mystery. The invisible war between cosmic construction and destruction continues across scales that span from quantum foam to cosmic horizons, shaping the destiny of every structure we can observe while operating through mechanisms we have barely begun to comprehend. Each measurement brings us closer to revelations that could unlock the deepest secrets of reality, while simultaneously revealing new depths of cosmic mystery that extend far beyond current human understanding. The mathematical symphony describing cosmic evolution grows more complex with each passing year, yet it also becomes more beautiful as hidden symmetries and unexpected connections emerge from the chaos of observational data. The universe reveals itself as far stranger, more dynamic, and more mysterious than any previous generation ever imagined, challenging us to expand our conception of what physical reality might encompass. As our instruments become more sensitive and our theories more sophisticated, we stand at the threshold of discoveries that could revolutionize physics as profoundly as quantum mechanics and relativity transformed understanding in the 20th century. The invisible universe holds secrets that might unlock technologies we cannot imagine, reveal connections between consciousness and cosmic evolution, and provide answers to questions about existence that have haunted human curiosity since we first looked up at the night sky. The battle between visible and invisible, known and unknown, continues to unfold through cosmic time while we struggle to understand forces so powerful they control the fate of every galaxy, yet so subtle they remain hidden behind veils of mathematical complexity that challenge the limits of human comprehension. The ultimate nature of cosmic reality awaits discovery in the darkness between stars, encoded in gravitational whispers and quantum fluctuations that carry messages from the deepest foundations of existence itself. The fundamental architecture of reality operates through mathematical principles so alien to human intuition that comprehending them requires abandoning every assumption we have made about the nature of existence itself. Recent theoretical breakthroughs suggest that dark matter and dark energy might represent different manifestations of a single underlying phenomenon that transcends our conventional understanding of space, time, and causation. Advanced quantum field theories propose that the vacuum of space itself possesses a rich internal structure populated by virtual particles that flicker in and out of existence with such rapidity that empty space seethes with invisible activity. These quantum fluctuations might create correlations between widely separated regions of the universe through entanglement mechanisms that operate faster than light speed, while somehow avoiding violations of relativity. The mathematics describing such effects push beyond conventional field theory into territories where space-time geometry becomes emergent from more fundamental quantum information processes. String theory calculations suggest that our familiar three-dimensional reality represents merely a shadow cast by higher dimensional structures that contain the true physics governing cosmic evolution. These extra dimensions might harbor forms of matter and energy that interact with our observable universe only through gravitational effects, appearing to us as dark matter and dark energy, while actually representing complex dynamics in spaces we cannot directly perceive. The mathematical description of such higher dimensional physics requires techniques so advanced that only a handful of researchers worldwide possess the expertise necessary to work with them effectively. Loop quantum gravity approaches these mysteries from an entirely different theoretical direction by proposing that spacetime itself has a discrete, granular structure at scales smaller than anything we can measure. In this framework, the smooth geometry described by Einstein's equations emerges as an approximation valid only when averaged over vast numbers of quantum spacetime units. Dark energy might represent corrections to classical gravity that become significant when integrated across cosmic volumes, while dark matter could arise from quantum geometric effects that create apparent mass concentrations where none exist in conventional terms. The experimental verification of such radical theoretical proposals requires observational strategies that probe physics at energy scales completely inaccessible to terrestrial laboratories. Cosmic ray observatories monitor particles accelerated by unknown astrophysical processes to energies that exceed anything achievable through human technology by factors of millions. These ultra-high energy messengers carry information about cosmic conditions so extreme that conventional physics breaks down entirely, potentially revealing signatures of extra dimensions or quantum gravitational effects. Precision measurements of gravitational wave signals provide another window into exotic physics by detecting ripples in space-time itself that propagate across billions of light-years while carrying encoded information about their cosmic origins. The interferometers required for such observations achieve sensitivity so extraordinary that they can measure distance changes smaller than 1/10,000th the width of a proton, while distinguishing genuine gravitational signals from seismic vibrations caused by ocean waves breaking on distant shores. Future gravitational wave observatories will extend detection capabilities into frequency ranges that probe cosmic phenomena operating during the universe's first moments after creation. These observations might reveal whether cosmic inflation was driven by quantum field dynamics that connect to dark energy through mechanisms we have never imagined, or whether alternative scenarios involving cyclic cosmologies or emergent spacetime provide better descriptions of cosmic origins. The mathematical frameworks required to interpret such observations demand computational resources that push against the fundamental limits of information processing. Quantum computers might eventually provide the calculating power necessary to simulate quantum field effects operating across cosmic scales, but such devices remain largely experimental constructs that exist primarily in laboratory demonstrations, rather than practical applications capable of solving cosmological problems. Advanced artificial intelligence systems trained on cosmic simulation data represent another approach to understanding phenomena too complex for human mathematical analysis. Machine learning algorithms can potentially discover patterns in observational datasets that reveal connections between quantum mechanics and cosmic evolution through purely empirical methods that avoid theoretical biases inherent in conventional analysis approaches. These artificial minds might recognize signatures of exotic physics that human researchers would never identify through traditional scientific reasoning. The convergence of quantum physics, artificial intelligence, and cosmic observation promises to revolutionize our understanding of invisible forces within the coming decades. Each technological advance brings us closer to breakthrough insights that could transform not only our knowledge of the universe, but our conception of what it means to exist as conscious observers in a reality where the vast majority of cosmic content remains forever hidden behind veils of invisibility. Yet perhaps the most profound implication of these investigations extends beyond their scientific significance to questions about the ultimate purpose of cosmic evolution itself. If the universe operates as a vast information processing system where dark matter and dark energy represent computational resources, then cosmic structure formation might serve functions we have never considered. The intricate patterns of galaxy clustering and cosmic web architecture could represent solutions to optimization problems operating across scales from quantum to cosmic. The emergence of consciousness within such a computational cosmos might not be accidental, but rather an inevitable consequence of information processing systems achieving sufficient complexity to become self-aware. Human intelligence could represent the universe developing the capability to understand itself through mechanisms that operate simultaneously across quantum and cosmic scales. Our scientific investigations might constitute cosmic introspection, where the universe uses conscious observers to probe its own deepest foundations. This perspective transforms the search for dark matter and dark energy from purely scientific endeavors into explorations of cosmic purpose and meaning that connect directly to fundamental questions about existence itself. Understanding invisible forces might reveal not only how the universe works, but why it works, providing insights into whether conscious observation plays necessary roles in cosmic evolution or merely represents accidental byproducts of physical processes operating according to mathematical principles indifferent to human curiosity. The answers we seek lie hidden within the quantum substrate underlying all physical phenomena, encoded in field fluctuations and space-time geometry that operate according to mathematical laws so beautiful and complex that discovering them represents one of the greatest challenges in human intellectual history. The invisible universe surrounding us holds secrets that could unlock technologies beyond current imagination, while revealing connections between mind and cosmos that might fundamentally alter our understanding of what consciousness represents in the grand scheme of cosmic evolution. The battle between construction and destruction, between forces that build complexity and those that tear it apart, continues to unfold through mechanisms that span from microscopic quantum processes to macroscopic cosmic dynamics. Every measurement we make, every theory we construct, every breakthrough we achieve brings us closer to understanding how these invisible titans shape the destiny of everything we can observe, while operating through principles that challenge the very foundations of human knowledge. The invisible titans that control our cosmic destiny continue their eternal dance across scales that dwarf human comprehension, shaping the fate of every galaxy while operating through mechanisms we have only begun to glimpse. Dark matter weaves the scaffolding upon which all structure depends, while dark energy drives an acceleration so relentless it will eventually tear apart the very fabric of space-time itself. These forces have battled since the moment of creation, and their struggle determines whether our universe ends in fire or ice. We stand at the threshold of revelations that could transform our understanding of reality as profoundly as quantum mechanics revolutionized physics. The invisible universe holds secrets that might unlock technologies beyond imagination while answering questions about existence that have haunted humanity since we first gazed upon the stars. The battle for cosmic destiny continues, and we are finally learning to see the war